I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Thank you for the students. Just pray you to guide our steps this semester. Just help these students do their best each day and just to focus on their studies. Lord, in your name I pray. Amen. All right, so just a few sort of big organizational comments. This is my schedule for spring 18, which is this semester, right? And my laser. All right, so basically I teach Math 422 at 8:15. I have an office hour from 9:05 to 10:30. Here, and here. That's my office is across from that those rooms with sinks. It also have physics lab in there, but mainly I think of those as rooms with sinks. And but I guess I'm actually teaching. All right, and and then I have office hours. I mean, I love physics. I just don't care for physics lab. I just think I have nothing good to say about physics lab. Anyway, and oh, okay. Yes, office hours here, 10:05 to 12:05 Tuesday, 9:30 to 12 on Thursday. Let's see here. Where are we? We are in DeMoss Hall 2054. And this is you guys. So we're going to meet from 1:05 to 1:55, 12:45 to 2, and such and so forth. On occasion, we'll skip a day. I'll announce that when that happens. And then this is my passion project. I don't know what you want to call that. It's an independent study with a couple students. My research actually has been on trying to generalize calculus, replacing real numbers with an algebra. I've been working on it for about 5 years and still kind of not sure where it's going. But in any event, let's see here. Well, if you're curious, I actually have links to the papers that I've written jointly with a couple of students over the last couple of years. And I'm pretty proud of those. Okay, enough with the, oh, a little bit more fun and games, just a second here. I really need to update these pictures. They're kind of old. Sorry for those of you who've had me before. You've seen these before, for the most part, I think. This is it's my daughter, Hannah. And, you know, I don't know. I think that's Matthew. It's really hard to tell at this point. I think that's Benjamin. That's definitely Benjamin. This is most certainly Matthew. He's upset because he was denied soda at the pool. That I remember. But I have 5 children, and they all kind of look the same when they're at various ages, so I need to label these, you know. Now I'm going to have to edit this video. Great. Thanks, guys. We were at Disney World at some point, and they got lightsabers, which was awesome. This is the Lego store at Downtown Disney, which is very nice. This is no longer existing, I guess. They've torn down the Honey, I Shrunk the Kids thing in Disney. It was in Hollywood, but that was a summer. I spent about 6 weeks building this in my backyard. It's a castle, and I have it down as like concrete down there. I spent like 3 days just digging the holes to put the posts in because we have hard-packed clay right under everything. It's horrible. Don't ever, if you find out that you're living in a house where there's like clay outside and you have this idea about digging a hole, stop. Just don't even bother. All right? Or hire somebody and pay them by the inch. Make sure to set it and make a contract before you actually let them work at all. Isaac is he's now 6, and I think he's about 3 or 4 in these pictures, but Isaac is hilarious. Daniel's my oldest boy. He's 9. Matthew is 4. Benjamin is almost a year old, and Hannah's 11. Here's some older pictures of Hannah. This is an annoying GIF that I leave because, I don't know, it's just fun. Let's see here. All right, enough of this fun and games. So we're in Calculus 3. This is the, another annoying GIF. What do you know? This is the website. And on here I have a bunch of stuff like your course planner that tells you day by day what's going on in here. This is a link to the the YouTube playlist, which I will add today too, before too long. And just various old solutions and so on. So probably most importantly is the course planner, which is also posted in course content alongside the less interesting and far more bureaucratically tainted syllabus. But this just has what you actually are interested in, which is more or less what we're planning to cover today, tomorrow, the day after, and so forth. These are my notes, which I will talk about more in just a second. Like I'm trying to cover pages 9 to 18 today, which is starting to seem impossible because I blather on about non-interesting things for too long, but I'll shut up soon enough. Anyway, any questions about this? This shows you the day by day for the course, what we're more or less covering. We have a test. Test 1 is apparently February 13th, so that will cover chapters 1 and 2 of my notes. You notice I haven't said anything about a textbook. Why is that? So my notes are the textbook, right, essentially. Now, at times you might want a resource, you might want to have a calculus textbook around. I would encourage you to make sure you do have a calculus textbook around. And my notes and the resources I have on my website are nice, but they're not, there's something missing, granted. But I certainly think that spending the amount of money our current book costs for the complete lack of scholarly detail it's a poor investment. I mean, I think you do much better to buy an old edition of Thomas or Anton or Stewart or Rogakowski. There's tons of really good calculus books out there. Any of those would be good. So I would just say for your personal library, it's a wise thing to have a good standard calculus textbook sitting there. And I would say that the one that's required for this course, technically speaking, in other sections is not a good choice. And we're working to change that. Okay, so anyway, there's that. Missions are required homework, right? Like mission 1 is due next Tuesday. What does mission 1 look like? I think I put it in course content, right? I think I did it a long time ago. I've forgotten how long it's been since I did it. Hopefully I didn't post the solution yet. That would be embarrassing. These are kind of out of order. Sorry about that. I don't know how that happened. Obviously, I want you to start with mission 1, right? Like, don't start with mission 8, just for the record, okay? Here, I'll fix that so we don't accidentally start with vector calculus by accident. Whew, that would be embarrassing, wouldn't it? If you can do the homework on vector calculus, then we can just hang it up and take a vacation the rest of the semester because you don't need the rest of the stuff. And vector calculus is the ultimate goal in here, and understand that. So if you could already do that, there's hardly a sense in meeting the rest of the semester. Some of you are thinking, let's try to do that now. I was at a community college, and we had quarter system, and one of our quarters, for whatever reason, had a Christmas break smack in the middle of it. So I was taking trigonometry, right? And we had like 2 weeks before the Christmas break. And so I just went home, and I did the rest of the homework for the whole course. Because, the book was fine. I can read it. I can do the homework, and brought it back. And we were also supposed to make a leader box that had 12 sides. No, we're just supposed to make a leader box, but because I like to be annoying, I made a 12-sided one. And I remember handing it in to my trigonometry professor, and I remember her looking at me and she goes, "You're single. And you live with your parents." I was like, it's true. It's all true. But then she let me just take the final, and I didn't have to get up at 9 on Monday, Wednesday, Friday the rest of that quarter. Rest assured, I rubbed that into the rest of the students I knew in my electronics program. Mahaha. Let's see here. Mission 1. I'm sorry, I actually do have math to teach you guys today. I do. So here it is. This is mission 1. Find the distance between these various objects. Calculate unit vectors and dot products and cross products and angles between vectors and things about triangles and show these identities. And anyway, here's all these problems they're due next week. All right. So I guess I better get to it. Yeah.
So you'll never have questions from the textbook?
There is no textbook. Yeah. Now, that said, I have mentioned that there is recommended homework, right? I'm sorry, I'll get with it here eventually. So this is my, these are the notes, right? And this is posted in your, where? Course content and also on the web page. The web page is, I mean, it's 15 megabytes, so I don't really, I mean, I think it'd be smart to keep a local copy, right? Because, well, sometimes the network here will just do like 15 megabytes, like, yeah, whatever. It's nothing to me, right? There are other days where it's like, it's something, it's 5 minutes of your time, right? So depending on where you are and what smart or dumb phone you're using. Anyway, so this is a searchable PDF. One of my pet peeves is when I have math battles in here and then I see people Googling stuff. It's like, I give you a searchable PDF. If you were going to search somewhere, please search my notes. I give them to you in free PDF format. Don't go to the Google and consult with the King. King doesn't know that much. Con. I mean, he knows some things. King actually knows quite a bit more than Con. But that's another story. And John can, wait a minute, do you know the, yeah. I mean, Con's a smart guy and everything, but he's not a mathematician, and so he has different things. Like for him, it's just what? How to push the stuff around. Is it really about understanding as much? Probably not, right? He's just trying to teach people a fast path to doing these problems in a way which will be accepted as correct. The deeper goal of understanding math as deeply as possible is not something that's necessarily on the table for a non-mathematician. It just can't be. It's not what they do. Anyway, I digress. You notice, though, this time is not wasted here. Right here, the course notes, and I would, if you click on it, right, it'll take you to there. So the table of contents actually has, it will take you to the different places. And the place where I'm probably going to get recommended homework for you guys is at the end of each chapter, much like a physics. Physics books always have the problems at the end of the chapter. I have adopted that style for these notes. At the end of every chapter, I have problems. And it's an old joke that mathematicians are only happy when they have problems. It's true, though. And so here's the problems. And some of these are like, like your homework. Some of them are like harder. Some of them are not. And you're like, well, that's great. You're not collecting them. No, that's true. I'm not collecting them. I will recommend you do some sometimes. All right. So like after class, I'm going to sit down and think about which ones of these I should recommend that you look at like today. Okay. So I'll send you an announcement about that a little bit later. Who knows? Maybe there won't be any in there that are really recommendable. Now you're like, well, that's great. So you've got this list of problems that you recommend I do sometimes, but only when you say so. I'm like, well, that's true. I'm going to tell you on a day-by-day basis which ones of those ones you should probably be looking at. And but part of the reason that that's friendly is because those problems actually are solved. The solutions are posted on the website down here. So like here's the solutions to problems 1 through solution to problems 1 through whatever 25 at the end of that first chapter of my notes. The solutions are all posted here. So the problems at the end of the chapters, by and large, have solutions posted on the website already. All right. So in some sense, better than a textbook in the sense that pretty much all of the problems have solutions, right? Is it possible that some of these are the same as the ones I'm actually asking you to turn in? It's possible. I don't have that good a memory. I don't remember which one I did when. So it's entirely possible that I have shown you the solution for one of the problems I actually collect. Now, if I did that, the point is not just for you to copy mindlessly. The point is for you to copy mindfully. I mean, you should try to think. The point of every homework problem is to understand something. It's not to get points. It's to learn. All right. Anyway, any questions? Let me click on the course planner, and then I'll just stop talking about this organizational stuff. We're almost done. So mission 1 is due next Tuesday. It's posted in course content. You can work together, but don't copy each other's work. All right? Talk about ideas, not line-by-line steps. All right? if the grader notices that you have copied from someone else, we take the grades and we take the number of points earned for that identical solution, and we, like, you know, if it was full credit, I guess each one of you get half credit. Let's see here. And then at some point, I'll just report you to academic conduct or something. But let's not get carried away just yet. Let's see here. That won't happen anyway. Do your homework. Cheating on homework is kind of like cheating on an assessment test. It's just dumb. I mean, placement test. Cheating on a placement test is the dumbest thing, right? Like, what if you, you're successful, and then you end up in the course that you can never pass? It's like this, like endless. It's just not a good idea. You're like, well, anyway, I shut up. There's an online. My brother teaches another place. He's also a math professor, and there they have this online placement test, and it's just, well, you can figure out what happens. It's not useful. But anyway, so test one is, did I already say this? It was the 13th. Maybe I already said this. I don't remember. But so for test one, we're basically talking about geometry in view of vectors and equations, and then we'll talk about the calculus of curves, and then a little bit about integration along a curve. The thing I wanted to warn you about is that this is the thing I was getting to. Grades. So it's kind of tiny. There are 4 tests. Each one of them is worth 120 points. So that's 480 points from tests. The final is 240 points. So whatever that works out to, 720, I guess. Missions, 120 points. There are 8 missions. Each one of them is worth 15 points. So I think that's, if I remember right, did I remember that right? At least 120. I might have remembered that wrong. There might even be, how many? Here, let me just check on that real quick. This is where teaching more than one course gets to me, is I forget, which system I used in which course, Let's see here. How many points do we? 120. Oh, so there are 120 problems. Each one of them is worth 1 point. I have other classes where the problems are worth 2 points or 3 points, depending on. So anyway, but in here, 1 point, and there are 120 problems, so you figure. So the missions are 120 points. Those are the turned-in homework. Math battles are 40 points. Math battle is basically an in-class group quiz right before the test, right? Daily quizzes is the new thing. That's worth 100 points. And participation, I'm pretty much going to give to everybody. If I don't give you participation points, that means that you have somehow annoyed me on a personal level. So I just keep those there just in case. I'm just kidding. Actually, maybe this semester I'm going to make everyone's 20 points contingent on everyone doing the survey, because I just looked at my stupid end of course. I mean, my very informative and useful feedback end of course evaluations, and I think I had an average of 3 for most of them. I mean, out of just, it didn't matter if the class had 6 people or 20 people. I'd like 3 do it. I don't know. It was, I think your calculus 2 had more. I think like 7 of you guys did it, but I can't remember. Maybe it was 3 though. I don't know. What I do know is that definitely no more than 40% of the students responded, and I think that's too high. And so I really would like to have a higher survey response. And so I figure, what if I make those 20 points contingent on everyone doing the survey? And then that would be communism. But then I also need to publicize who hasn't done the survey yet for maximum effect. That probably violates various federal laws. But it'd be fun, right? It'd be fun. I don't know. I haven't figured. And I hear you guys. I get really tired every time I buy anything. Can you fill out a survey on such and so forth? It's like, shut up already. Just leave me alone. I don't want to fill out your survey. So I feel I hear you. But anyway, I'll shut up about that. Any questions? All right, I'll shut up. Let's talk about math. put this away. So, first couple classes will be mostly talking about vectors and geometry. Show of hands, who in here has had Physics 231? All right, who has not had Physics 231? All right, so for all you guys, you're at a steep disadvantage. And when everyone else in here besides you guys is going, yeah, do not take anything from it. It's just that they've already seen this stuff before. So relax. You're not alone. There are you see those people who just raised their hands who haven't had it. It's going to be okay. But at the same time, do not be fooled. These other people, they've just seen this before. So, and for those of you who've seen it before, I'm sorry if it's confusing. So Rn is notation for the set of n tuples of real numbers. So x1, x2, xn, such that x1, x2, xn is a real number. All right. This is, I often refer to this as Rn, right? Or n-dimensional Euclidean space. A lot of times, of course, R1 is just plain old real numbers, right? R2, often we think of as the plane. This is the set x comma y, such that x and y are real numbers. Now, you could express R2 as a Cartesian product if you wanted to. You could also say, hey, this is really just minus infinity to infinity, Cartesian product with minus infinity to infinity. And some people would write that minus infinity to infinity squared, but which kind of makes sense, right? R2, which is just r squared. R3 is the set x, y, z, such that x, y, and z are real numbers. These sets are the blank canvas on which we build geometry and calculus, all right? They're our canvas, where we're going to paint math. What would R4 be? You might use T, X, Y, Z. I mean, you can, or you could add a W if you wanted, You got lots of choices. Now, why do we think about Rn? What's the point? Well, R2, I think you're most familiar. I mean, the real numbers you probably don't think about that much, but we're always using them, right? R2, well, that's naturally identified with the plane, right? What's the picture? This is y, this is x. You pick a point, a comma b, right? That's what? This is an element of R2. So naturally, R2 is a nice thing to use to describe something that has sort of just 2 degrees of freedom and it's like a plane, right? How about R3? What would a picture for R3 be? Well, usually we use something like this. X comes out of the board, Y goes like this. This is kind of an artist's rendition. I mean, you can't really draw 3 dimensions on 2 dimensions, right? But that's our best, well, that's my best picture. So I think of X is coming out of the board, Y going that way, Z going this way. So if I take a point here, say A, B, C, that's a point in R3. Now, to try to give you some kind of perspective about that, it's useful to look at projections of this. Right? Like here, this point would be the projection of that point onto the xy plane. What would the coordinates be to that projection there? A, B, 0. Very good. Right. And then you could look at the projection of that point onto the xz plane, right? What would this point be, projecting that point? A0, 0, yeah. And then, of course, we could also look at the projection of that point in the xy plane back to the y-axis as well, right? What would this point be? 0, 0, B, 0, right? All right. I suppose we could do the same kind of thing in the plane itself, right? Like the two-dimensional plane. So this projection down to the x-axis is what? It's A0. And of course, this one over here is what? It's 0b. So a lot of understanding of Cartesian coordinates has to do with projecting the points in Rn back to coordinate planes or axes to sort of take it apart piece by piece, right? Now, in 3 dimensions, I mean, maybe we're a little bit less familiar with, we could set up a 3-dimensional coordinate system in this room, right? Like I could say that the z-axis is this wall over here, right? So then I would say that John over there is in the positive x direction, all right? And then this would be the y-axis, right? Say along the line, you know? And then like we could go over here to Nathaniel and try to find the coordinates to the top of his head right here, right? So he'd be in the first octant, as it's called. It's where x is positive, right? Where y is positive. And we have to pick a system, like a system of measurement, right? So if we use meters, what? It's about something like 2 meters from the corner. Maybe this is about 4 meters this way. And sitting down, I guess it's about 1 meter to the top of your head, right? So the coordinates to the top of his head would be something like, what did I just say? 2, 4 in the y, and 1. Right? So given a point in 3-dimensional space, if you can construct a coordinate system, then you can make a unique correspondence between these triples of points and the actual points in physical space. Now, it's a philosophical or perhaps a physical problem whether or not you can actually construct such a coordinate system, right? But the success of Newtonian mechanics testifies to the fact that much of everyday existence can be, in fact, modeled with 3-dimensional coordinate systems, right? And you're like, well, isn't that enough then? Right? There's 3 dimensions. Like, have you ever been walking around and all of a sudden another dimension opens up for you and you're like, oh man, I was going to be in class in time, but then I got stuck in the 4th dimension. Like, it doesn't, I mean, it might be claimed sometime. I probably respect it, but not usually common to our experience. So like, why do we study higher dimensions then? They are theoretically useful, right? So it's not hard to come up with very real physical things which involve more than 3 degrees of freedom. Like, for example, you could take this robot arm and take another robot arm on it and take another robot arm on it, and suppose basically that those are universal ball joints that are free to rotate in any different which way, right? So basically, if you just set up a little sphere based on the center of that ball joint, it takes 2 sort of spherical angles to tell you which direction, right? So this point out here, P, would depend on, let's say, theta 1, phi 1, theta 2, phi 2, theta 3, phi 3, where I'm saying that theta 1, theta 2 is from, the theta 1, theta 2 has to do with the orientation of this first robot arm, and then theta 2 and theta 2 and phi 2 has to do with the orientation of the second robot arm from that point. And then this theta 3 and phi 3 has to do with the orientation of this robot arm relative to that point, right? I can set up coordinate systems at each one of these universal ball joints, right? And so I would need 6 parameters to describe that robot arm, right? So it's entirely possible that a 3-dimensional robot could bring you to a question of the calculus of a path in 6 dimensions. It's not at all hard to find problems like that. Here's one. And there's really no limit, right? You can just keep adding robot arms, and every time you do, you get a couple more dimensions, right? So thinking of dimensions as real spatial physical dimensions, of course, is our happy place, but that's not all that there is. There's so much more than that, all right? Okay. All right, so then, vectors. 2 dimensions, you pick a point, right? Well, that naturally corresponds to a directed line segment, like this. So my convention in here, guys, is to say that a comma b is identified with the vector a comma b. Like, so, interpretation, all right? So here, I'm thinking of this as being a point. Here, I'm thinking of this as being a directed line segment, which is what we call a vector. For the most part, we adopt the physics convention in here that you can move vectors around. So this vector A, right, is a directed line segment, and I could move it other places, like over here, you know, and it would still be the vector A, but now it would have a different base point. So let me say this is P1, this is P2. So base point P2, base point P1, which is, by the way, the origin, right? So there's obviously a natural identification between points and vectors based at the origin, all right? But as long as you maintain the direction and the length, you can move them around, and we still think of them as being the same vector. But you should understand that when we do that, we're basically saying, well, we don't care about the base point. We're just going to look at vectors without a base point. And that's done throughout physics. Yeah.
Just the little symbol on top of the A just means it's a vector.
Yeah, that means vector. Yeah. Okay, so A is a vector. And let me just, a little bit more language here. A, I would usually do something like A1, A2, like that. This is a vector. I can write it as follows. I could also write it like this, A hat. So this A would be the magnitude of A. This would be the direction of the vector A. This is pretty typical physics notation. In mathematics, a lot of times, rather than, I mean, math commonly, especially my notes also, will use A. Magnitude is the length of A, like this. All right? The magnitude of the vector. So the first order of business is, if we have a couple of vectors, how do we add them? Can we scalar multiply them? How does that work? All right? So let me just kind of draw that for you. So if I have a vector like this, A, and I have another vector, B, I'll draw it over here for just a second, like this, all right? Suppose I want to add them. Geometrically, how we understand this is by what's called tip-to-tail addition. So we take this B and we put it like this, essentially. All right? So this is how we add vectors tip to tail, geometrically. And then so the sum of the vectors, geometrically, is this guy. Or you could say the resultant of A plus B. So geometrically, this is how we add vectors. How do we do it with algebra? So this point would be A1, I mean, excuse me, yeah, well, this vector would be A1, A2, right? This vector B would be B1, B2. What's the vector A plus B? I heard A1 plus B1, A2 plus B2, yeah. Indeed. So we add vectors algebraically by adding components. Now I drew the picture for 2 dimensions because that's my happy place. But it's equally, I mean, here's a definition. If we have a vector V plus a vector W, then the ith component of that is the ith component of v plus the ith component of w. Or oftentimes, if we have, aka, if we have v is equal to v1, v2, vn, and w is equal to w1, w2, wn, then vi is just vi, and wi is just wi. So like the ith components of v and w are just vi and wi respectively. And in that notation, we just have this v plus w I is equal to vi plus wi. But that's the algebraic way of doing it. All right. Geometrically, that corresponds to tip-to-tail vector addition. How about scalar multiplication? What would it mean by? Well, think about this. If we have a, right, and then we do a again, right? So then this should be what? A plus a, right? But what should a plus a be?
2A.
Surely it should be 2a, right? And what would that be? That would be 2a1, 2a2, using my notation for a being a1, a2. So that is scalar multiplication by 2. If you think about it, multiplying by a negative number will turn the vector around, right? Anyway, so let me just give you a definition. If c is a real number, then cv, the ith component, is just c times vi. So when we scalar multiply a vector, we multiply each component the same way all across the board. All right. Anyway, I have to talk about these things, but you guys almost never have trouble with this part of the discussion. So we start at 105, we end at 205, right?
155.
Dang it. All right. Well, next time I will talk about vector components and stuff. I see I talked too much about life today. My bad. Sorry. I'm behind. There will not be a daily quiz tomorrow. We're going to have to wait till Wednesday to start that. All right? I don't think I've gotten far enough to actually assign you a problem. So, yeah. That's another good reason to delay the daily quiz till Wednesday, because it's hard for me to notify the myriad of you who are not in the Blackboard yet. So.